While I put this away, if we can have the other panelists, we've got Andrea Gallo, our CEO, we've got Dr. Bao from the Beijing Institute of Open Source Chip, and we've got Stefan Volantowicz from the Munich University of Applied Sciences. So Andrea will be chairing this talk, which is going into the last 15 years of RISC-V, experiences from around the world, from Krista from the very beginning, and also from Stefan and Dr. Bao about their experiences of how RISC-V developed in both Europe and China.
Krista, on May 18, 2010, you told us earlier this morning that on that day you received a special email. Can you tell us how it all started?
Yeah, we've been looking at different ISAs to build our research infrastructure. And like Andrew Waterman was one of the principal grad students looking around at instruction sets, also Yunsub Lee as well. But Andrew was the one who's going to have to do most of the work. And so when he was looking for an existing ISA that was reasonably simple, that he wouldn't have to do a lot of compiler software work for. So eventually he came back and said, we need to do, this is a day or two before, he said, I think we should do digital alpha. So now the problem with the alpha was it was already a dead instruction set. So commercially it had gone away. And a lot of the software support, there was still a reasonable amount of software support. There was obviously a specification already. But I sort of discussed with Andrew and said, look, there's all these features we really don't want in alpha. Like it was, we did want a 64-bit instruction set. That was the primary thing we wanted. But we also wanted a 32-bit, which alpha did not have. We didn't want to deal with, alpha had these features like trap barriers for floating point, and the original architecture didn't have byte and half word load stores. There's a lot of problems with the alpha architecture. So as I sort of went down the list with Andrew, at some point he eventually gave in and said, okay. And that was when he sent the email on May 18th saying, okay, I give up, we should go do a new one. So that was really the birth of RISC-V that day when we decided to go ahead and do a new one.
I have a question for Dr. Bao. How did you get to know about RISC-V in China?
Yeah, so I was introduced to RISC-V I think it was in 2014. At that time, I was a member of the editor of the largest Chinese computer magazine under the China Computer Federation. So one day I received an email from a friend at UC Berkeley, and in the email he said, "So can you publish a paper, a Chinese article, a Chinese translated article?" The article actually entitled RISC-V, the instruction set should be free, the case for RISC-V. I think, Dave Peterson and Krista, you guys probably wrote the article in August 2014. Yeah. So then this article was finally published in the second issue of 2015 on that magazine. I think this was the first public appearance of RISC-V in China. Yeah.
And for you, Stefan?
Yeah, so I was in the Open RISC community, which was one of the other ISAs that Krista mentioned, and we had an annual conference in 2014, which I think was the year that Krista, you did the tour of outreach. And we had Alex Bradbury from reaching out and saying they have this new project called Low Risk, and they are doing open source silicon, and if they want to participate in this event, and they are bringing 3 people from Berkeley. They have their new ISA, and everyone was a little bit skeptical, to be honest. But we were very happy. It was Andrew and Yunsub and Krista showed up at our event. It was at the time, I think, like 20 participants. Like this was everyone who was interested in open source ISAs at the time, I think, in Europe. And the next year we had it then in Geneva at CERN, right? And I remember like it took like half a day until OpenRISC was mentioned for the first time, and there were like dozens of RISC-V implementations, all open source, and I think the rest is history. Yeah.
I was going to say that talk at the WildConf in 2014 is on YouTube, so you can look at that first talk in Munich back then in Europe.
Yeah. It was very exciting. I think at the time, like it felt really like, okay, these guys, they know what they're doing. We should listen to them. They have some history in RISC, and we were really glad. And I think the presentation, like fundamentally, is not much different than what we see today.
I remember in one of my first conversations with Krista, you shared that initially you were using it mainly to teach computer architecture to the students, and then you realized that it was being used beyond. Can you tell us more how you all came to realize that something big was happening?
Yeah, I mean, we did build it initially just for our own group to use for research and for teaching. And so actually we started in May 2010 doing the design, but by August we were teaching a class using RISC-V. And, you know, the poor Berkeley undergraduates, they had this very unfinished, very raw design, but that's what they're used to at Berkeley. So they worked with us and helped make it better. And so then we used it in classes, but as we were changing it, the spec would be changing because we had more experience with it. But also we would change it sometimes for a problem set. So we'd have a question in the class, what if we added this instruction? How would you write this code sequence? And then I think we had some engineer from India, I think, send us an email saying, why did you change the specification? And I had to explain to him, but this was just for a class project. It was, you know, and then we started realizing other people were depending on the spec. And we had to be more serious about having a fixed version of the spec. But for us at that point, it just been a local tool that we were using to teach classes and build research chips. Yeah.
And I have a curiosity. Is RISC-V the only one that does not use flags?
No, like MIPS did not use flags either. So there was, I think a few other, I don't think Alpha did either. So the more streamlined RISCs did not use flags. Yeah.
Okay. So that's one of the differences coming from the RISC revolution. And Dr. Bao, you are leading the one student, one chip. That's amazing. How did it start, and tell us something?
Yes, so one student, one chip is, the initiative is for the talent education. And so this is, I think we should thank to the RISC-V since, in China, before 2020, we have found the shortage for the chip design talents. But how to educate those talents? So actually, we follow the philosophy learning by doing. However, without RISC-V, it seems like there is no good path to fulfill this goal. So, for example, one of my students many years ago, he actually proposed to build an open source ARM CPU core on the web on the internet, and many students supported the proposal and wanted to join, but finally he got a legal warning from ARM. Since this is illegal thing without ARM's license, it is even you have the ability to building a CPU core, but you don't have. There's a legal issue. But RISC-V allows every student to create their own design. So this is I think the benefits of the open source, the open standard. So then in 2019, I launched the One Student, One Chip initiative, and the idea, the goal is to make the undergraduate students to build real chips. So the first term, there are 5 undergrad students participating in the initiative, and now it's already in the 6 years. Already there are more than 10,000 students covering from 800 universities participate in this initiative now. Yeah.
And And Stefan, I see that in Europe, in universities, RISC-V is ubiquitous as well. How do you see it? Is it across all universities? Do you see different poles? How is the situation in Europe, and how is it growing?
I think in European universities, it's pretty much well adopted nowadays. Like we still see like this multiple instances where people just didn't have the time yet, I think, to move from other ISAs. But I think the value promise that you get with the entire open ecosystem, a lot of reference designs, ready-made courses and everything, that's a very good value promise that you don't get by other ISAs. I think in terms of adoption, it was like pretty much the earliest use, right? R&D in academia and industry and teaching, I think, in Europe, pretty early adopted to RISC-V. And I think over the last years, we saw tremendous growth, I think, post-pandemic especially. I think during the pandemic, people found a little bit more time or like more focus. And we see a lot of those courses now also shared, I think, which is a very good use of time also.
And Stefan, you were mentioning the growth over these last 15 years. And I think one of the missions from academia is also to incubate new initiatives and then bring them to products and the industry. So over these last 15 years, how have you seen these evolving for RISC-V?
I think initiatives, like especially from the Zurich Bologna team on the PUL platform, like they played a very critical role in the adoption of RISC-V in Europe at least. I think also had some impact globally. And I think this is one of the strengths of Europe, right, that we have strong universities that also like they are mission driven a little bit, right? It's not about the one R&D project or the one paper or the other, but building like a sustainable platform that people can use and share. I think this had a very big influence. I think what we saw also from other universities, but I think this is one of the highlights definitely we should always mention, because I remember like having discussion with Pulp in 2013 about using OpenRISC, and then we had a discussion a year after, and I think RISC-V was really able, and I think, Christy, you can say like the commercial traction around 2014 was somewhat on the horizon, but I think the adoption in academia was very important for Europe, because from this we saw bootstrapping of the projects in the European Union now in 2017, 18, 19. But all of them based essentially on the strong academic background in RISC-V, I think, that we have in Europe.
And for China, do you also see this transition from academia incubating into products and industry?
Yes, I think so. RISC-V in China is fast growing, and both academia and the industry, they devoted their efforts in RISC-V. But for academia, people mainly focus on like research using AI, like AI assistant chip design, and also like talent education. And also we launched in academia launched some like open source projects, for such as like Shangsan projects. But for the industry, they began adopting RISC-V many years ago, and there are a lot of products, RISC-V based products in China. But most of them are for like the embedded scenarios, embedded applications. But we can see that over past years, RISC-V has been using high-end scenarios. So this is so the industry, they have the intention of collaboration with they start looking at some like open source projects, just like the Linux kernel, open source Linux kernel in the open system area. So then the BOSC was founded by a bunch of companies together, and to support the open source RISC-V core project. Yeah. So this is, I think this is a good example of the transition between the open source project launched by academia and to the industry products. Yeah.
And Krista, this morning in the State of the Union, you went through some of the key moments from the technical side. From your perspective, which have been the moments that you enjoyed the most? And when was it that you also felt that you were enabling this transition to products in industries?
Yeah, I'm trying to think of some of the highlights. I think one of them was actually the first RISC-V workshop. So we did the rollout at Hot Chips, and we got a lot of positive feedback. So we decided, so at Berkeley, we have a tradition of doing research retreats where we go away for a few days somewhere and take all the students and the industrial sponsors and we'll get together and have a very intensive 2 or 3 days. And we decided to add 1 day for a RISC-V workshop in Monterey. The retreat was going to be in Monterey, so we added 1 day. I think for me, what was exciting was, like I said, in the video's still up there, when you hold a party, you don't know who's going to show up, right? So this first RISC-V workshop, the first thing was it sold out very quickly. So we had 140 people, I think, showed up. But the thing that I thought was very exciting was there was 40 different companies came. So it wasn't really academics as much as industry came, and they came en masse. And that to me was one of the highlights. The other one was at that event, Rumble, Aaron from Rumble, he said, look, we already shipped RISC-V commercially. So in 2015, the first workshop, we found out RISC-V was already shipping commercially. So that was another sort of highlight in the RISC-V story. I think later, the big announcements, like when Western Digital said they were going to be using it, that was a pretty exciting time back in 2017. And then before that with NVIDIA, decided they'd selected RISC-V to replace their own internal core. That was also a big highlight to me. I think it's just these things, seeing, because we're all engineers, we like seeing people use our stuff. So these are the highlights when you see that somebody's really using it and enjoying it. That's the highlight.
And where do you see RISC-V in 15 years from now?
In 15 years, that's a long time. So I think it will then be obviously the dominant ISA. It will have replaced a lot of others. I think people will be very surprised at the reach in 15 years. Yeah, 15 years is long enough that a lot of the software ecosystems will have changed and RISC-V will be dominant. Yeah.
Yonggang, where do you see RISC-V in 15 years?
Yeah, I think 15 years is quite a long time, so it can happen. Many things can happen. So I expected to see RISC-V could be the largest the Chico ecosystem in the world at that time. Yeah.
And Stefan?
15 years is a long time. I think it's very, it's not really debatable, RISC-V will be everywhere, right? What I'm curious to see, and this is probably what I would predict, is that RISC-V also plays a role in creating more innovation in chip design in general, which we already see a little bit, like geopolitical challenges aside, but you see a lot of innovation stemming from RISC-V and RISC-V enabled designs. And I think I would see RISC-V even in a larger, broader ecosystem. I'm, of course, an open source advocate, but in general, something that essentially changed the industry, right, and made a transformation into a new E1000, essentially, away from traditional semiconductor habits to a new way of designing chips, building ecosystems on chips, focusing on software, hardware, interfaces, etc. I think this is what RISC-V really enabled to me, and I see it being very dominant in 15 years in this domain.
Do we have time to go for any questions from the audience? I'm checking with
yes, we
Andy.
have.
So anybody has any curiosity, wants to ask any questions? One here.
Thank you. I'm an architecture engineer from Star5. We are developing RISC-V based CPU. So I have a question, general question for the vector extension. So we know it's a very important component for the RVA23, but in the development we met some difficulties, because especially the vector load store in the vector extension is very flexible. It didn't limit the stride size, and the segmentation load has a lot of patterns. I have a question: so why? What's the initial idea of design a vector extension like this? And do you have any suggestions for the hardware producers to implement this? How to comply to the vector extension? Thank you.
Yeah, I think I'll take this. So, yeah, the vector extension is complicated, and it was beaten out over many years. I think one thing I'll call out specifically is the segment load stores, which are the most complicated part of the vector load store unit. The trouble is they're very useful, and so all our software people, if we don't have those, they complain. And you'll see some of the other architectures have the same kind of instructions. So if we didn't have those, we wouldn't be competitive for some functions. And yes, they're difficult to implement, but multiple companies have built working microarchitectures for that. It is hard work, and I think as we look to future extensions, I think one of the things I'm very cautious about is adding more complexity to the vector load store in particular, because it's quite complicated already. But yes, I empathize, I feel for your pain. I think many of us who've looked at implementations also have looked at the pain of doing this. But I will say that, like, for example, at Sci-Fi, we have teams that have built in order and out of order versions of this. They solve the problem in different ways, and engineers are creative. But I think that the only thing I'll say to make it feel better is the software people really appreciate having those instructions. Yeah.
Any other questions anywhere? I can get up there if you need me to.
I have a question to Krista. So vector was it wasn't your PhD, but your postdoc topic, right? Was it like a special feeling for you once you started RISC-V and thinking, okay, now I can put all my thoughts into a new ISA, like that's my new sandbox that I can play in?
Somewhat, yeah. So vectors was my PhD thesis, vector microprocessors, right? And but to me, it's this more general thing of you have to find in ISAs, if you want an ISA to live for a long time, you have to find the right primitives that are going to work in one generation across different microarchitectures, but also as technology evolves to keep going. And vectors to me was clearly one of those things that was going to be a central component. Like I talked about this morning, I think in RISC-V, it's, you have scalar, vector, and now matrix is the next sort of thing we're doing. Less about the specifics of individual little ideas, but it's just thinking, how are we going to make software keep running better as we do future machines? And also, how do we, in one generation, reuse the software across different implementations? And if you start thinking about architecture that way, there's only a few ideas that really survive the test of time. And vectors is one of those. And it goes back to, Cray in the 70s, really. He really figured this out. But yeah, to me, it's a powerful primitive that's a necessary part of computing. And I think the other thing is when I did my thesis, that was the second wave of neural nets. So that was I think neural nets, every 30 years, there's a wave. So in the 1960s, it was perceptrons. There was one wave. In the early 90s, it was backprop being rediscovered. That was the second wave. That's when I was working on this. And it was clear the vectors are the right way to support neural nets then. And now we have the 2012 AlexNet, deep learning, this wave. And again, it's like GPU, which are kind of like vector machines running it. Yeah.
I think we have another question here.
Yeah, thank you. I'm Henri Pierre-Charles from CA. My question is more on the software side. On one side, there is a lot of evolution on the RISC-V architecture with tensor, matrix multiply. On the other side, there is a lot of evolution on the software ecosystem for PyTorch, the high-level application. But in between, there is a lot of difficulties to adapt at the compiler side, the length of the vectors, the new instructions. So I don't know what exactly is my question. What is the best language to use the RISC-V, or is it a way to take benefit of the RISC-V at the language level?
I think we can mention the ratification of the RISC-V vector intrinsics for the C language. I think that would be the right answer.
Yeah, I think for the AI frameworks, there is like MLIR, IRI framework is one example where people are building the stack to target RISC-V. Some of the other AI stacks are more GPU focused, and they're really not very good, like the XLA stuff. But I think MLIR and IRI stack is a better pipeline to get from neural net graphs to RISC-V high-performance implementations. And I think you saw several, I think it was a presentation this morning from Andy's, the Sci5 is also doing this, using that framework to do the mapping to RISC-V cores.
Any more questions?
Up there.
One right at the back. Bear with me.
Hi, I'm David from Qualcomm, and I was wondering, RISC-V, RISC-V is a specification that evolved a lot. At the beginning, it was quite simple, and my question is there any implementation that has been that has been ratified that now you kind of regret the way it is, and that you wish you could do better? Speaking of like the ISA, like sorry, the encoding or the privilege spec.
Sorry, I didn't quite get the question.
So, Christy, I think the question was if you want to remove an instruction.
Oh, but
Yeah, or change them.
things we wish we did differently. Yes, there's many, many things. But I think none that are so terrible that we rip it up and start again. I think, yes, I think there's two levels of mistake. One is later on you think, oh, we really shouldn't have done that, and we should have known at the time we shouldn't have done that. The other one is nobody would have known that, 10 years later, you'd want to do this other thing, and your decision then is maybe suboptimal. So that's knowing everything you know now, you could go back in time and decide you should have done something a little differently. That to me is a very excusable mistake. How would you have known, right? But at the time when there's several choices and you wish you made it differently, there's many of those, but none of them are that important in the grand scheme. That's the other thing. If we stop to make everything perfect, we never finish anything. So you have to commit and move on. So one of the things in architecture is, software is king, right? So you have to give them a base and not change it. And so you have to always be backwards compatible, 100%. You don't get to undo, which is why we try and be very careful when we ratify new things. But nothing's perfect, so we will make mistakes. But you just have to live with them, and part of the art is, in the later extension, working around any mistake you might have made in the old one, right? And being creative. But the reality is, I think the commitment we make to the software universe is we're not going to change things. So you have to stick with it and move on. But yes, there are many mistakes we would have liked to change, but I'm not going to talk about them because people then start putting in proposals to change them.
One last question I think we've got time for. Anyone?
Can I ask a question to Christy while you're walking down? I remember from the presentation at OrConf, I think you said the ARM architecture manual has 1,500 pages. It doesn't make any sense. Last time I checked, I think we're getting near to this now. What have you learned about ISA design, and did you have any wrong estimations about the complexities, or is it more on the how to organize it?
Yeah, I think this is something people don't quite sometimes we get people don't understand why we did things the way we did. One of our specific goals was to make the base very small, but complete. So the idea was the 40, 50 instructions you need, they should be all that you need to make a C compiler work, and be very straightforward. And there's several reasons for that. We wanted to make a self-consistent small set, which wasn't available in any of the other ISAs. So none of the other major ISAs, that was not a concern for them. But for me, it was a concern because I wanted to be able to teach the instruction set in one lecture and teach an implementation in the second lecture. So in 2 hours, I could tell you the ISA and show you how to build it, right? And GCC would run on it, deliver code for it. So that to me was a goal. So but the modularity came from that, knowing that if we design this core this way, we can always add on the other features later. But in terms of teaching, you have this very simple base. Also, the second reason was when you're building accelerators, which was when we designed RISC-V, the project was all about specialized computing. What we realized was we always need to have a C compiler first. So what's the minimal thing you need to have a C compiler? And then you can add on whatever else you wanted to on the side. But that idea of a very simple base, both for teaching and for research, that wasn't a goal of the commercial ISAs. Right, so whether we'll probably end up with more instructions, the other ISAs, because more people will be using RISC-V in more places. Yeah. So it's not a goal to have not a lot of instructions, but it is a goal that base survives 15 years' time. That base should still be being used in schools to teach computer architecture, because then I don't have to change the slides and other people can use the same slides every year. Right?
So how many pages for RISC-V specification now? So initially, I think there are 200 pages for base. Yeah.
Well, I think one thing that's happening, people, when we wrote the spec initially, we wrote it as a rationale, not as a reference manual. We wrote it as explaining the ISA and why we did it. But people want a reference manual with 1 page per instruction, and that makes a lot of sense. But when you have hundreds of instructions, you end up with hundreds of pages. But when we give the rationale for his 27 instructions that are all just variants of his theme, you can describe it in a few lines. And that was the style of the original manual. So you understood the structure of the design, but it was not very good as a reference manual. Right? If some assembly, you see some assembly code, what does this instruction do? You have to go searching in the manual. So I understand. I think it's fine. I think we should have thousands and thousands of pages of documentation where each different people have different views on the documentation, like how they want to view the spec. But I would like to keep the tutorial so if people who really want to understand the design can read, maybe 10 pages will explain the core of the design to them, right?
I think we are running a bit out of time. I think everybody has enjoyed this conversation, and please join me in thanking Krista, Yungang, and Stefan. And happy birthday, RISC-V.